Have you ever really stopped to think about the physics that's happening all around you? I mean, every time you catch a ball or, way more dramatically, when a car's safety features kick in during a crash. Well, there's this hidden language of motion that's literally governing our safety, and in this explainer, we're going to decode it.
It all kicks off with a really simple question, one you've probably experienced yourself. Why is it that when you jump and land, bending your knees hurts so much less than landing with your legs locked straight? The answer feels intuitive, right? But the actual physics behind it is, honestly, brilliant. And here's the wild part. The answer to that simple question about jumping is the exact same principle that engineers use to design airbags, padded dashboards, and those crumple zones that make modern cars so much safer. We're going from a playground hop to life-saving technology, all with the same bit of physics.
So, let's treat this like a bit of a mystery. Our mission is to figure out the secret behind making any stop a safe stop. And to do that, we're going to need 3 key tools from the physics toolbox to crack this case wide open.
Okay, tool number 1 is momentum. It's a concept that goes way back. Physicists like Isaac Newton even called it the quantity of motion, which is a pretty cool way to think about it. And it is the perfect place for us to start. So what is it really? Well, linear momentum, which we usually write down with the letter P, is basically how hard it is to stop something that's moving. I absolutely love how some of the sources describe it, an object's unstoppability. It's all about how much mass an object has and how fast it's going, all wrapped into one idea. And the formula? It's beautifully simple. Momentum equals mass times velocity. So an object's unstoppability comes down to just 2 things: how much stuff it's made of, that's its mass, and how fast that stuff is moving, which is its velocity. And importantly, since velocity has a direction, momentum does too. It's what we call a vector.
To really get a feel for this, let's look at an example. A big football player, say 110 kilograms, running at 8 meters per second. You do the math, and he's got a momentum of 880 kilogram meters per second. That is a whole lot of unstoppability. You would not want to be in his way.
Now let's compare that to the football he might be about to throw. Even if that ball is flying through the air super fast, say 25 meters per second, its tiny mass means its momentum is only about 10. That's it. The player has almost 86 times more momentum. It just goes to show you what a huge part of the equation mass is.
Okay, so we get momentum. It's the state of motion. But how do you actually change it? Well, that brings us to our second tool, impulse. This is the secret ingredient, the thing that connects a force to a change in momentum.
Impulse, at its core, is the change in momentum. But it's really about how that change happens. It's the effect you get when you apply a force over a certain amount of time. You can think of it like a push or a kick, but one that has a duration. It's not just instant.
And this right here is the master key to solving our entire mystery. It's the impulse momentum theorem, and it says that the force you apply, multiplied by the time you apply it for, equals the change in momentum. This means a huge force over a short time can do the exact same thing as a tiny force over a long time.
Okay, we've got our tools, we understand momentum, we understand impulse. It is time. Let's put them together and solve the mystery of the safe stop. This is that aha moment we've been waiting for.
All we have to do is just rearrange that master equation a little bit. If we solve for force, we see that force equals the change in momentum divided by the change of time. And that little bit of algebra reveals the crucial relationship. See, to bring something to a stop, the total change in its momentum is fixed. You can't change that. But what you can control is the force, by playing with the time it takes for that change to happen.
And this right here illustrates the solution perfectly. In a hard stop, think hitting a brick wall, the time of impact is incredibly short. And because time is on the bottom of our equation, a tiny time means a huge force. But on a soft stop, with an airbag or by bending your knees, you are increasing that impact time, and a longer time means a much smaller force. Same change in momentum, completely different and much safer outcome.
Let's put some real numbers to this so you can see how staggering the difference is. Imagine a car's momentum drops to 0 in just 1/10 of a second. The impact force from that would be a jaw-dropping 1 million newtons. That's just an enormous, unsurvivable force.
But now, let's imagine that same change in momentum happens over 5 seconds, all thanks to crumple zones and airbags doing their job. Suddenly, the force plummets to just 20,000 newtons. Now that's still a big push, but it's way more survivable. The takeaway is simple. By stretching out the time of the stop, we slash the force. That is how safety features and bending your knees save you from getting hurt.
So we've solved the mystery of the safe stop, but you know what? The story doesn't quite end there. To really get the full picture, we need to bring in another character in this physics play. It's one that often gets confused with momentum, but it's just as important: kinetic energy.
Kinetic energy is simply the energy of motion, but right away there's a huge difference from momentum. Unlike momentum, kinetic energy is a scalar. That means it has no direction, just an amount. It's really a measure of how much work or damage an object can do just because it's moving. This table lays out all the differences perfectly. Just look at the formulas. Kinetic energy depends on velocity times squared. This is a really big deal. If you double an object's speed, you double its momentum, sure, but you quadruple its kinetic energy. Also, check out the conservation rules. Momentum is pretty much always conserved in a collision, but kinetic energy, not so much.
And this leads us to different kinds of collisions. You've got your perfect, bouncy, elastic collisions, like billiard balls hitting. In those, both momentum and kinetic energy are conserved. But in most real-world crashes, what we call inelastic collisions, things bend, deform, or even stick together. Momentum is still conserved, but a lot of that kinetic energy gets turned into other things, like heat, sound, and of course, damage.
So let's end with one last thought puzzle for you. It is entirely possible for a tiny, super-fast bullet and a massive, slow-moving truck to have the exact same momentum, the same unstoppability. But which one has more destructive energy? The answer is hiding in that crucial difference between momentum and kinetic energy, and it reveals exactly why speed is such an incredibly important factor when we talk about safety. Something to think about.